It's based on a Chemsims project, which was a National Science Foundation project that was focused on how to use simulations in class. The learning objectives for this particular activity is that we want you to be able to better understand when ionic compounds dissolve in solid, that they actually break down into their ions, and that's what causes them to conduct electricity. We also want you to understand what happens when covalent compounds dissolve in solution. And lastly, we hope that you can understand how and why substances dissolve in water based on how they're actually interacting. In order to explore the topic of solubility, we're going to use this PhET simulation, which was sugar and salt solutions. Let's begin by adding some salt to the solution here. Here we can see the crystals of salt fall into the water, and notice that we see nothing change apparently with the water. Let's do the same for sugar. And when we add that, we see nothing that macroscopically appears to change. Instead, we get a homogeneous solution where both the sugar and the salt are now dissolved in that water. So let's take a moment, we'll remove both of those, and we're going to add this conductivity meter. Now let's see what happens when we add the sugar. Right now we can see that the light bulb is dark, so the water by itself isn't conducting any electricity. As we add in the sugar, we again see no change with this conductivity meter. We'll remove the sugar, we'll swap over here and add some salt. Let's see what happens when we do this. As we add the salt, we can see that this representation is trying to show us that the conductivity meter, that light bulb, is lighting up. And the more salt that we add, we'll actually see that those lines will grow in. We'll have more of them. That's suggesting that this is actually now being brighter and conducting electricity better. In order to understand what's happening and why this is different, we actually need to go over to this micro tab. Let's add some sodium chloride to the solution. Here we can see those crystals of sodium chloride drop into the solution. And once they get there, what we see is that breaks down into the ions. So the ions of sodium and the ions of chloride separate. It would be good to think about how this actually would then influence the ability of this solution to conduct electricity. Okay, so we'll remove the solute there. Let's switch this over to sugar. And we'll add in some sugar crystals. And let's see what's different in this case. What do you notice that's different when we added the sugar versus the sodium chloride? Hopefully you're noticing that here we have the individual molecules of the sugar that are still attached together, though those molecules obviously have separated from each other. And so this is something that's different between the dissolution of sodium chloride and the dissolution of sucrose. And again, think back to how that might actually influence which of these two solutions conducts electricity. To understand even further, though, let's click on this water tab. Wow, there's a lot of action going on here. So let's pause this for a moment and try to see what's happening. In order to understand this, we have to recognize that here we've got our water molecules. Each water molecule is comprised of a red oxygen and those two white hydrogens. And if we look at this, we might start to see that there's some orientation that tends to happen in this space. That typically what we have is we have our white hydrogens that are near or attracted to those red oxygens. In order to understand that, we can click on this and we can see the partial charges here. And so here we can see that we've got this partial minus that's on the oxygen because it's a more electronegative atom. And we can see these delta pluses on the hydrogens on other molecules getting near that. And if we look throughout this, we'll find that pattern seems to be repeating throughout. So let me get rid of that for a moment and let's look and see what happens if we add some salt to solution. So we'll get those guys moving. So here's our sodium chloride. Again, we've got the chlorine ions that are green and the sodium ions that are pink. So we'll put this in solution, we'll see what happens. And what we see in this case is we might start to see a little bit of orientation that's happening. If we look closely at the sodium ion, we notice that this obviously has its plus charge. And what do you notice about the oxygens that are around them? Okay. Is there a preferred orientation for the water in that particular case? Well, what if we look over here? Similarly, what if we look at those chloride ions? Do we see a particular orientation that those waters seem to be pulling up? In order to help us see that, we can look at the partial charges here, and you might start to see a little bit of a trend of which of those charges might be attracted to those ions. Okay, so let's reset that. And now we'll do the same thing, but this time we're going to look at what happens when we put the sugar molecules in water. So if we take our sugar molecules and we put them in here, we'll again see them start to separate. It's a little bit of a slow process. It takes a little bit for those water molecules to get in between them, but now we can see they've made their way in there. We're starting to separate them. And if we give them longer, they'll continue to push further apart. So we might wonder if there's any sort of orientation here. It's a little bit hard to tell right now because you've got your sugar molecules that are labeled here. I'm going to remove the sugar highlights using this box here. And that will be able to show us just a little bit more what's going on. Here we can see these gray atoms are the carbons. We still have the red oxygen atoms that are part of those sugar molecules. So you can see some of those red atoms like here and here. And these guys over here are actually coming from that sugar. And then we also have some hydrogens that are on that as well. So we might want to try to look a little bit closely and see if we see any preferred orientation. Again, I'm going to turn on the water partial charges. That will help us to be able to see the difference. So if we look at this oxygen right here, that's part of this sugar molecule, do we see any particular orientation of the waters? Or if we look at the hydrogen that's hanging out right here, that's on this oxygen, that's part of that sugar molecule, do we see any particular way that that's interacting with the waters? Hopefully you do. Hopefully you're seeing a little bit of interaction that's going on between those water molecules and the delta pluses and delta minuses that would be on the sugar as well. Because remember, that hydrogen-oxygen bond is going to be polar no matter what kind of molecule it's in. So as we think about this, hopefully now we have a little bit better understanding of why and what kind of interactions might be going on that would be allowing either salt or sugar to be able to dissolve in water. I would encourage you to go and download this simulation. You can find the link in the notes below. And there's an opportunity to play a little bit more. I would encourage you in particular, you can click over here on this micro tab. There's a whole variety of different solutes that you could explore. And you can see some of the differences that happen when you look at different kinds of ions that are dissolving in solution. You may find this helpful as you're exploring these things, or if you want to look at what's the difference between sucrose and glucose, for example. So lots of opportunities there. So thank you again for paying attention to this video that comes out of the Chemsims project.